We do record. Okay, today is the 29th. We're going to do lines in space. We're going to do tangents as well. When you have two lines in a plane, you have basically three possibilities for two lines in a plane. They could be parallel, they could be the same line, or they could intersect. In space, they could be parallel, they could be the same line, they could intersect, but yet there's a fourth possibility for the two. They could be, what are they called?
A wormhole. A skew.
A wormhole. No, skew lines. All right, they could be skew lines, which are non-intersecting, non-parallel lines. So we have that possibility for lines in space. All right? Well, what we are concerned with is generating an equation for a line in space. So here's what we're going to do. We're going to do this. We're going to be given a point. Let's call x sub naught. I know it. Y sub naught, z sub naught. And we're given what's called a direction vector. And what we want to do is find the equation of the line in space through this point parallel to that vector. Okay, this here. Okay, that's what we're looking to do. Well, let's see. If a point is going to be on this line, let's say Q, and have coordinates x, y, z, what must be true about vector PQ? Well, vector PQ, which is equal to x minus x sub naught, y minus y sub naught, z minus z sub naught. If those two vectors are going to be parallel, vector PQ must be a constant multiple of v. That's how you know two vectors are parallel. One's a constant multiple of the other. Okay? Therefore, x minus x sub naught, y minus y sub naught, z minus z sub naught is equal to k times our direction vector ABC. And if we multiply through by k, we get x minus x sub naught, y minus y sub naught, z minus z sub naught is equal to ka, kb, and kc. And if these vectors are going to be equal to each other, it must be the case that x minus x sub naught is ka, y minus y sub naught is kb, and z minus z sub naught is kc. Finally, x is equal to x sub naught plus ka, y is equal to y sub naught plus kb, and z is equal to z sub naught plus kc. This is called a parametric form for the equation of a line in space. This is the equation of that line in space. It's called a parametric form because it's in terms of a parameter k. There's another way to express this. It's called a symmetric form. This is parametric form. There's a symmetric form which is less useful. I think the web assign will mention this, though, symmetric form. What you do basically is solve for k in each of these. X minus x sub naught over a, that's equal to k. Solve for k here and you get y minus y sub naught over b. And you solve for k here, you get z minus z sub naught over c. This is called a symmetric form for the equation of a line in space. Like I said, it's not as useful as our parametric form. One thing you have to be careful about with this parametric form, there are an infinite number of ways to express this. Okay? Well, let's do a problem with it. What we should be able to do is, given 2 points in space, find the equation of the line through those 2 points. Let's take a look at that. Is everybody else set with this? Not yet? Okay.
So those equations over there are parametric? And those
This is the parametric form. This is the symmetric form. It's the parametric form we're going to use almost exclusively. The only reason I mention this is I think Rebbesign perhaps mentions this in one of the problems. But you know what? What you can do is instantly change the symmetric form by just setting it equal to k and change it from this to this. Okay? Multiply by a, add x sub naught. That solves for x. And do the same for y and z. Alrighty. How you doing, Dave? Omar? Oh, you okay? Okay. Let's fundamental thing, possible test question. Give you 2 points, find the equation of the line. It's a fundamental exercise. Let's do it. So, let's take 2 points in space. I don't know. Let's take 1, 2, 3. 1, 2, 3. Let's take this point. And let's take another point. How about 0, 5, negative 1? 0, 5, negative 1. Okay. Call that Q. And let's find the equation of the line through these 2 points. Okay? Find the equation of line PQ. Well, first thing to do is find a direction vector. Our direction vector, V, is going to be equal to vector PQ. And that's going to be equal to negative 1, 0 minus 1, 5 minus 2, and negative 1 minus 3. Okay. What's the equation of that line? Here we go. Here's one form of the equation. X is equal to, take any point, let's take this point P, 1 minus K. This minus K comes from this right here. This is the A, B, and C. Y is equal to 2 plus 3K. Z is equal to 3 minus 4K. That's the equation of that line. Okay. Can someone give me another form, forget the symmetric form, another form for this line using this parametric form, but that looks different from this one?
Minus K. K is 1 minus X.
K is 1 minus A, that's true. It's solve for K. Now, not quite what I want. What I want you to do is change something, either this, these coefficients, these constants here, these constants here. So, is the question too nebulous?
2 minus 2x equals 2 minus 2k?
2 minus 2K. Oh. I don't know. If you wait a second, you're saying 2 minus, multiply this side of it by 2, and then you would do 4 plus 6K here? I don't know. Does that work? I don't think that can't work, can it? What's that? I know. I'm thinking that's not going to work. But I'll tell you what will work. If you do 1 minus 2K, watch this, and 2 plus 6K, and 3 minus 8K, that works, believe it or not, just multiplying these by 2. That does work, okay? But if you multiply these by 2 as well, that may not work, okay? Why does this work?
That's just the length of...
Yeah, that's it. It's still the same vector, but twice the length, but it's still the same direction. So that does work. In other words, when K is 0 here, you're going to get the point 1, 2, 3. When K is 0, you still get the point 1, 2, 3. When k is 1 here, you're going to get the point 0, 5, negative 1. That's this guy down here. For what value of k will you get the same point 0, 5, negative 1?
1/2.
It would be 1/2. At k equals 1/2, you're going to get 0, 5, negative 1. So it's a different value of k. What that does is change the speed at which this particle would move along a line if we were talking about its velocity, okay? By making this go twice as fast. What else works? Changing the initial point. If you take any point on this line, it works here, okay? Any point. Doesn't have to be 1, 2, 3. 0, 5, negative 1 works, or take any other point on there. So there's an infinite number of ways to express that line, okay? All right, how are we doing here so far? 2 points, find the direction vector by finding the vector through those 2 points and using one of the 2 points. Gives you the equation of the line. Now, another fundamental exercise, if you think back at linear equations that you did in Algebra 1, is the relationship of those 2 lines. Are the 2 lines parallel? Do they intersect? Okay, are they the same line? And here in space, we've got that 4th possibility of skew lines. So if you were to be given 2 lines, you ought to be able to find the relationship between those 2 lines. Okay, you ready? Let's do it. Well, you don't seem excited, though. You're ready, but are you excited about this, Eric? No, huh?
Mentally, yes. Physically, probably not showing it too
Oh, okay, all right, that's okay. All right, so let's do 2 separate lines here. And this is, I'm pretty sure this is a web assign exercise as well. Let's say L1. Wait, does somebody have a web assign exercise there? No, that's all right. Well, I'll just make one up. Okay, line 1 is, let's say x is equal to 3k, y is equal to 2 plus 2k, and z is equal to 1 minus k. And let's say L2. Now, if I use L2, I'm going to have to change my parameter here to something else. Let's see, use S, say. Oh, how about 2 plus s, y is equal to 2 minus s, and z is equal to 3s. I don't know, I'm just making these up. Okay. So now we have 2 lines in space. Okay. Change the k to give you points on this line, change the s to give you points on this line. We want to know the relationship between these 2 lines, okay? First of all, could they be the same line? Is it possible they could be the same line? Just by looking at this and making some... No, they can't. Because of the direction vector. This direction vector here is 3, 2, negative 1. This line is parallel to that vector. The direction, you call it V1. V2, this direction vector, is 1, negative 1, 3. These are not a constant multiple of each other. They are not going in the same direction. If your direction vectors are not parallel, they can't be the same line. Not only can they not be the same line, these 2 lines are not parallel to each other. Okay? Just because of that. If this one were 6, 4, negative 2, they could be parallel, they could be the same line. Okay? But because they're not a constant multiple of each other, they cannot be parallel, nor can they be the same line. But we could have 2 lines that are intersecting or skew. Okay? And this is what we're going to do. We're going to determine that. How do you determine if they're intersecting or skew? Well, here's the deal. You're going to find a value for this parameter, k, and this parameter, s, where 2 of the 3 coordinates agree. Say your x's and y's, where they agree. Where the x's and y's agree, we're going to see if the z's then agree. If they do, they intersect at that point. If they don't, they're skew lines. Okay? Because where x and y's agree, one is over the other, or they intersect. So that's what we're going to do. You ready for this? Let's do it. Here, x is equal to 3k. We're going to set that equal to 2 plus s. The y here is equal to 2 plus 2k. We're going to set that equal to 2 minus s. We're going to find out where x and y are equal to each other. Then the lines will either be above each other or they'll intersect there depending on the z coordinate. So 2 2 equations and 2 unknowns. Tell you what I'm going to do. I'm going to add up these 2 equations. I'm going to get 2 plus 5k is equal to 4. 5k equals 2. Oh, great problem. K is equal to 2/5. Okay. When k is equal to 2/5, my x in my first line is equal to 6/5, and my y is equal to,
12 fifths.
what is it?
12 fifths.
12/5? All right, I'll believe you on that. Okay? 4/5.
Maybe 8
Oh,
fifths.
no.
On the first one, on this y's here. I don't think it is. That's 4/5, that's 10/5.
So 14.
Yeah, I'd say 14/5. Okay. That's on the first line. That's on L1. You with me on this? Everybody okay? Dylan, how you doing? Okay? You okay? All right, because I don't care about these other people. All right, so.
Wow.
Oh, man. All right. Anyhow, L2. When k is 2/5, let's find out what s is. S is equal to, at this time, well, if k is 2/5, put in 2/5, you get 6/5. Subtract 10/5, you get negative 4/5, I think. Is that about right? I think so. Okay, just take the k, put it in here, 6/5, put a negative 4/5. That's 10 minus the 4, 6/5. Okay, so that does work. All right, let's find the x values for L2. They should be the same as these, but let's check it out, because you never know what could happen here. X is equal to 2 plus s. It's 10/5 plus the negative 4/5. That's 6/5. Good deal. Is everybody okay? Okay. Y is equal to 2 minus s. It's 2 minus this. It's 2 plus 4/5, 14/5. So the x's and y's are the same at that point. So we either have the lines going like this, or they're going to intersect there depending on the z coordinate. So let's check it out. Let's find the z coordinate in L1. The z is equal to 1 minus k, 1 minus 2/5. That's 3/5. That's what the z coordinate is for L1. For L2, what's the z coordinate for L2? It's 3s. It's 3 times a negative 4/5. That's a negative 12/5. They are different. That tells you, me, all of us, they are skew lines. Okay? That's the kind of thing you have to do. Okay? Any question on that? If these z's had been the same, they would intersect at that point too. Okay? You ready to go on? Okay. Liam, is this okay?
Yeah. Could you do it with like your y-z plane and then see if your x, or do you always start with your x, y?
I always do x, y, but you could do any two out of the three. Do x, z's, do y, z's. Sometimes it may be easier to do one as opposed to the other. I got to tell you that I almost always start the same way, but you can do it any way you want. Don't.
So because the z's are different, they're skewed lines, is that what you said?
The z's are different, that means they're skew lines. Okay? X's and y's are the same. So what happens? That's the time they're the closest to each other, when the x's and y's are the same. So this line would be directly above it. Okay? As a matter of fact, the distance between the two lines would be the difference in the z coordinates. If that difference is 0, the z's are the same, okay, and the two lines intersect. But if that distance is whatever we found the difference in the z's to be, one z was 3/5, negative 12/5, that difference is 3. Take 3 minus the negative 12. That tells me these two lines are 3 units apart here at that point, where the x and y's are the same, which is the distance between those two skew lines. How do you measure the distance between skew lines? It's precisely at that point where the x's and y's are the same. Okay? That's what it is. Okay, how's that look? All right.
Draw a picture of skewed lines just to see what it looks
A
like.
skew line? Okay. Okay, here we go. it's tough, because in two space, they always look like they, oh, wait, I can do it. Okay, watch this.
Would it be helpful to do it in free space?
What's that?
Would it be helpful to do it in free space?
Yeah, that's definitely what you want to do, but watch this. I can do this. I can make it so it's clear. Okay. See, if you did this, watch, if I do, I was going to do my parallel pipette thing here. Let's do this, rectangle here, and let's do, okay, watch this. I can do this. I can do this. Okay. Wow. I'm getting there. I'm getting there. I'm going to get this thing here. Okay. Here we go. So we have this thing. An example of two skew lines would be this line and this line. That would be an example of skew lines.
So they run, their paths intersect each other.
No.
But there's a distance between them.
Oh, okay. All right. I hesitate to say there.
Distance between them.
Yeah, there is. Yeah, they don't intersect. They're not parallel, non-intersecting.
I meant they run perpendicular to one another, right?
Well, I hate to say that too, because when you say that, it looks like they do this. That's perpendicular to each other. If they don't intersect, they're not perpendicular to each other. I mean, if you were to drop this one down to the plane here, maybe they are. But I wouldn't say they're perpendicular to each other. I would say they're non-intersecting, non-parallel lines. That's, I think, the best way to do it.
Okay.
All right. And I think that illustrates it there. In this room, for example, you could do it in this room. If you take this line up here, okay, and that line down there, those are skew lines. That line up there, ceiling and front wall. That line over there, side wall and floor, skew lines. Okay? Non-intersecting, non-parallel. Okay? All right, how are we doing? Doing okay? Jared, you doing okay? Okay. Yeah.
How did you know that the X and Y components were going to be, or the K's were going to be the same with the K and the S? Did you,
Wait.
on the last problem,
On the last problem, I just made up.
like something that would be,
I just made them up. What I did know is that they weren't going to be the same line or parallel because of the way the coefficients were. But I didn't know if they were going to be skew or intersecting or not. And I do know for any two lines, you'll always be able to find the X's and Y's are the same, except if you've got perpendicular lines to the axes. That could be a problem. Okay, if you got this line here with this line here, the X's and Y's are never the same. But if you have any other two kinds, they will have X's and Y's the same. So you got to
so
be
you just found K and S and then you plugged it in for Z.
correct. That's exactly right. Yes.
What if the Y value was the same?
Say that again.
The Y value, what if you had the same Y value?
The Y values are the same.
No, for the L1 and L2, for the N1 and N2.
For L1 and L2, the Y values are the same at 14/5. Both Y's are 14/5, and both X's, okay, are
Oh, that's Z. That's
6/5.
I'm talking about Z. That's Y.
Z. Okay, what about Z now? If they were the same, the two lines would be intersecting. The two lines would intersect. Say that again?
If they intersect, that's like perpendicular to each other.
If they intersect each other, yes, they'd have a point in common. That point would be the XYZ that you just found. Because each line contained that point, XYZ. Okay?
Do mathematicians have a preference for the cursive Z over just the regular Z? 'Cause
Yes.
It seems like that'd be confusing for people who are starting to learn this stuff. Because they look kind of the same, Y and cursive Z. I don't know, it's just me.
I think it's just you, Dylan. No, I don't think it's just you. It's the way, I don't know, it's the way I've always done it. It would be tough for me to break that habit of that cursive Z on that.
Do it just for Dylan, please.
Well, doesn't it kind of look like a line?
No,
Well, kind of, sort of.
Why was it?
It's got this thing here, this thing that automatic. The other Z with a little line through it there that people make. If you just use the Z by itself, I guess you could. But I got to tell you, after all these years of doing, it would be very difficult to me to.
Well, that's fine.
convert.
Well, plus
It's like
then we might think it's a 2 because now you're.
Yeah, I
changing
know.
from
Look at that.
cursive
It's a
Ds
2,
to other
but-
ones that- yeah.
I don't know about other math teachers. I don't know what they do. I'm not sure.
There are others.
That's a good answer. Wow, that was a really good answer. Now I think about it even more. Yeah. Okay. Good call. All right, let's go on. We got one more thing to do, and that's to do planes. All right, we got planes in space. Okay. All kinds of planes. What's that?
AC-130s.
AC-130s are up there. Yeah, you got all kinds of stuff. All right. 737, 747, 787, Dreamliners. You got, yeah, you got all kinds of stuff. F-15s, all right, all kinds of stuff. All right, let's do planes. All right, here we go. Let's see. Let's how are we going to define a plane? Let's do it this way. What's that? What?
It's got an aerofoil.
I thought it was a larger ass area.
It's all the
It's just
above.
average. It's just an average thing.
Okay. Here we go. We're given a point. And we're going to be giving a normal vector, okay? A normal vector to the plane. And defining the line, we were given a direction vector parallel to the line. Here, what we're doing is giving a normal vector to the plane. So, we want to find the equation of the plane containing this point and normal to some vector. The normal vector. Okay? Let's say that's ABC. Okay? That's what we want to do. Well, we're going to do the same thing we just did. How do we know if some other point Q, whose coordinates are x, y, z, is on this plane? Well, here's how we know such a thing. If we take point Q, it must be the case that vector PQ is perpendicular to our normal. Because when you have a normal to a plane, here, let's do this.
I don't know if I can go touching my stuff so much.
Whoa! What's that? Oh, you're all sick and stuff.
Yeah, I'm sick as hell, dude. Get away from my stuff.
Holy
Yeah, wiping it
moly.
all over your clothes is
Oh,
totally.
oh no! I touched my eye and stuff. Oh, forget, I'll use my own.
Oh god, you have to use your own pen?
All right, here we go. Here's this plane, and we got a somewhat wimpy. No, there we go. Yeah, we got it. We got it. And we got a normal vector. Now, what's true about a normal vector to a plane? What's true is, if you take some other point, whoa, geez, no matter what that point is, all the points in the plane actually, and you draw vectors or lines to the point of intersection, what's true about all those lines in our normal vector? How are they related to the normal? They're all perpendicular to the normal vector. That's what it means to be perpendicular to the plane. It's perpendicular to every line in the plane drawn to the point of intersection. So to be on this plane, it must be the case that all those vectors are normal to this one, or perpendicular to this one. Okay, that's got to be the case.
So P would be the
Put
center.
that right back in there, somebody can reuse it. So P what?
P would be the center of that rectangle.
First, well, not the center, because first of all, the plane keeps on going infinitely, so there is no center. But what must be true is that PQ in order for Q to be on the plane, it must be true that PQ is perpendicular to the normal vector. So PQ is this. This is vector PQ, just like we did before with the line. Must be perpendicular to our normal vector ABC. Now, how do you know when two vectors are perpendicular or normal to each other? What must be true?
They share one.
Yeah, sure.
What's that?
Can you ask that again?
Here's the question. How do you know if two vectors are perpendicular or normal to each other?
Cross product equals 0?
No. The
Dot product.
dot product is equal to 0. So here's what has to be true. The dot product of these two vectors, PQ and N, must be equal to 0. Okay? In order for a point to belong to this plane, it must be the case that that vector PQ is perpendicular to N, and if it's going to be perpendicular or normal to N, the dot product must be equal to 0. Well, let's see. What does that mean? It means that this dot this is equal to 0. That means A times x minus x sub naught plus B times y minus y sub naught plus C times z minus z sub naught is equal to 0. And guess what? Believe it or not, that's the equation of a plane. Okay, right there. Usually what's done, it's ax plus by plus cz equals d, where d would be a x sub naught plus b y sub naught plus c z sub naught. This is the equation of a plane. Okay, a, b, and c are the components of the normal vector. Okay, d is made up of the others, but we'll do a problem. Okay, that's the equation of a plane. It's pretty cool. As soon as you know the equation of a plane, you know its normal vector automatically. It's the coefficient of x, y, and z. Okay, so let's do a problem. What's
D equals D exactly?
D would be equal to, and this is not going to be all that useful, but D is ax sub naught plus b y sub naught plus c z sub naught. That's not going to be all that useful. D is some constant. Okay. What is important is the a, b, and c are the components of the normal vector. So, what do you think we should do? How many points determine a plane? 3. 3 non-collinear points determine a plane. 3-legged stools don't wobble, okay? Because those 3, they could be tilted, okay, but they don't wobble. 4-legged stools could wobble, okay? But a 3-legged stool will not wobble because the 3 points will determine a plane, okay, and not wobble. Just telling you. So here's the fundamental exercise. Here's a test question, okay? Given 3 points, find the equation of the plane, okay? So the last one was given 2 points, find the equation of the line. This one is given 3 non-collinear points, find the equation of the plane. So let's do it. Let's take 3 points. Good stuff. Let's find 3 points. I don't know. Somebody give me 3 points. Don't make them ridiculous, though. I don't want fractions. Go ahead. Give me a point.
1, 1, 1.
1, 1, 1 is good. 1. Let me see if I can actually draw it. 1, 1, 1. There's 1 point. Yep.
2, 2, 2.
2, 2, 2. 2, 2, 2. 2, 2, 2. Now, if you give me 3, 3, 3, there's no plane through those points. Those points are collinear, okay? And there's no plane. What was the other one? 1, 3, 5. Okay. 1, 3, 5. I don't know, up here somewhere. Who knows? P, Q, and R. 1, 3, 5. We want to find the equation of this plane through those 3 points, okay? Okay, here's what we're going to have to do. We have to find a normal, and we need a point. We have 3 points. We have plenty of points. But we have to find a normal vector to the plane. How do you find the normal vector to the plane? If we find a normal vector to PQ and PR, these two vectors, and we find its normal, that normal is the normal we need that's perpendicular to the plane. Well, how do we find a normal vector to 2 other vectors? What do we have to do?
Set their dot product equals 0.
No! Find the cross product. That somehow was poetic that it worked out that way. All right, we have to find their cross product. The cross product of 2 vectors is a vector that's normal to the 2 given vectors, and that's what we have to do. So we're going to find PQ. Okay, PQ, that vector is 1, 1, 1. We're going to find vector PR. That's going to be 0, 2, 4. Okay. I'm going to cross these guys. One, 1, 1, 0, 2, 4. That cross product will be my normal vector. Let's see what we have here. Cross this out, cross this out. We've got 4 minus 2. We cross this out, cross this out. I'm going to have 4 minus 0, but it's the middle one, so we have to take its opposite. Okay. And then we cross this out and cross this out. We're going to get 2 minus 0. Okay. We get 2, negative 4, 2. I'm going to make I'm going to divide by 2 and make it 1, negative 2, 1. Okay, that's my normal. You can always take a constant out, simplify it. Okay, and now I have a normal vector, and I have 3 separate points. The equation of this plane is equal to 1 times, now what I could use point, let me use point P, x minus 1 minus 2, y minus 1, I'm using the coordinates here, 1, 1, 1, plus 1 times z minus 1 equals 0. Okay? These are the components of my normal vector. These are the coordinates of my point. So the equation of that plane is x minus 2y plus z equals, I've got minus 1 here, plus 2, that's plus 1, minus 1 is 0. Wow, that's pretty cool. Okay, is 0. Does that work? Let's see if it works. The point 1, 1, 1, does it make it true? 1, 1, 1. Yes, it does. The point 2, 2, 2, does it make it true? 2, 2. Yes, it does. 1, 3, 5, does it make it true? 1, 3, 5. Yes, it does. All 3 points are on this plane. Therefore, this is the equation of that plane. What would happen if we used, instead of using 1, 1, 1, we used 1, 3, 5? Would we get a different equation? No, we would not. Thank you, Alex. Here we go. Let's try it. We got 1, negative 2, 1. We got 1 times x minus 1 minus 2 times y minus 3 plus 1 times z minus 5 equals 0. It looks different. When you multiply it out, it's going to be x minus 2y plus z equals, we got negative 1 plus 6 is plus 5, minus 5 is 0. What else does this say? This says the origin is part of this plane. So my diagram is not that bad. It should be tilted more because it comes down and hits the origin. 0, 0, 0 is also on this plane. Okay? How are we doing? Doing okay? Okay, now let's suppose this is the case. You're an engineer and you're designing something, and that something you're designing includes a wall that comes in at an angle to, say, this floor or the horizontal, okay, horizontal plane. And you want to calculate the angle that this plane intersects the XY plane. This dihedral angle, it's the angle of elevation of that plane. How could we figure out that angle of elevation of this plane, say, with the XY plane, which could be an important thing? Or, alternatively, let's suppose we have two different planes intersecting in a line, and we want the angle between the two planes, that dihedral angle. That's what a dihedral angle is. How could we do such a thing?
Protractor.
That would be one way. That's a possibility, but we don't have a protractor, so we need a better way. What's that? I want the angle of elevation of this plane with the XY plane. How could we do such a thing?
Some sort of math.
Yes, that is correct.
Trig functions of some sort?
Well, yeah, we're taking it, we have the mechanism, we have the ability to do this, but you got to think about, you know, these two planes. Okay, here, this plane here, say, intersecting the table, say. And we want this angle here. This is the dihedral angle we're looking for. We don't have any way of doing an angle between two planes, but we do have a way of finding out an angle between.
Take the outside vector.
Yeah, take the two normal vectors. Take this normal vector and take the normal vector of the table, and the angle between the normal vectors, guess what? Is the same angle as the angle between the two planes. That's what we do. So let's do it.
So it was math after all.
Yeah, it was math, yes. So here we go. We have our normal vector, 1, negative 2, 1. We have the normal vector to the xy plane. That normal vector to the xy plane is, what vector is that? Call it N2. What's the vector normal to the xy plane? K. Ha! Yeah, 0, 0, 1. Okay, 0, 0, 1. That's vector right there. If this x-axis, y-axis, z-axis, 0, 0, 1 is the vector normal to the xy plane. Okay? We want to find the angle between this vector and our normal vector. Called it N1, I guess. 1, negative 2, 1. How do you find the angle between two vectors? The cosine of that angle is equal to their dot product over the product of their magnitudes. Okay, this is 1. This magnitude is 4, 5, 6. The square root of 6, right? That cosine is 1 over the square root of 6. So it's a dot product, 1, over the product of their magnitudes. That magnitude is 1. This magnitude is the square root of 4, 5, 6, square root of 6. The angle then is the inverse cosine of 1 over the square root of 6. Somebody have that in radians just for me quickly? Because the way, and we know it's tilted like that. 1 over the square root of 6. I don't know. It looks, depends. I don't know.
I got 65.
Yeah, 65.9 degrees. Yeah, that's good. 66 degrees approximately. That could very well be. It comes in, and I know it contains the origin, so it is kind of a slant. Okay?
1.15 radians?
Yeah, that's about right. That's just about right. 1 radian, about 57 degrees. That's about right. A little bit off, but not too bad. Okay. One last thing. We've got two planes in space. How are these planes related? What are the possible relationships of two planes in space?
Manufacturer.
They could be what?
Manufacturer.
Yes, it could be related by manufacturer. It could be Boeing. It could be Airbus. It could be, yeah. What else? How else could they be related?
Parallel or
They could be parallel,
The same plane.
same plane. What else?
Intersecting.
Intersecting.
Perpendicular.
Right there, that would be intersecting. They could intersect in a line. Could two planes in space intersect in a point?
Only in 4D or above.
All right,
Yeah,
there you
it's time to
go.
this guy.
That's it. They couldn't intersect in a point, but they could intersect in a line. They could be the same plane, be parallel planes. That's about it, though, right? No such thing as skew planes, because they have to intersect somewhere, unless they're parallel. Okay, so let's say we have two planes.
Oh, that's easy.
Yeah, that's pretty simple stuff. Let's take two planes. And let's see if we can determine what's true about these two planes here. Let's take the P1. Let's say x plus y plus z is equal to 10, say. Plane 2. Let's say it's 2x minus y plus z is equal to 2, say. And we want to find out about these two planes. We only have these possibilities. Parallel planes, same planes, intersecting planes, okay? How can we determine whether they're parallel planes, for example? Yes, exactly. Look at the coefficients. This normal vector would be 1, 1, 1. This normal vector, 2, negative 1, 1. These are not constant multiples. They're not parallel to each other. Therefore, these two planes are not parallel, nor are they the same plane. If they were the same plane, one vector would be constant multiple of the other. So they are intersecting planes. How do two planes intersect? They intersect in a line. Could we find the line of intersection of these two planes? The answer is yes, we can find this line of intersection. We've got two equations, but three unknowns. You solve those kinds of equations by using a parameter. That's the very parameter like the k and the s we used from before. Let's watch this. Let's tell you what. Let us add up these two equations and eliminate the y. So x plus z is equal to 10. Okay. I'm sorry, I didn't do that right. I'm sorry. Add them up to get 3x plus 2z is equal to 12. Okay? All right. Eliminate the y's. And then what I want to do is I want to get one of these in terms of the other. So let's do that. Oh, this is going to be messy here, but we can do it. So 3x is equal to 12 minus 2z. X is equal to 12 minus 2z over 3. I'm going to let that equal t, or k, or s, or something. Yes?
We could even subtract those equations and find another
Oh,
equation.
wow. That's pretty good. If we subtract, the z's will go out, and then we'll have x's and y's. And then,
Solve those equations.
yeah, that's still going to give us the same thing. I don't think that's going to be any advantage, okay? But here's what I'm going to do now. If I let x equal t, okay, solve for z in terms of x. So z is equal to, okay, so x equals t. So 12 minus 2z is 3t. Okay. Subtract the 12. Negative 2z is equal to negative 12 plus 3t. And divide by negative 2. So z is equal to 6 minus 3 halves t. Okay? So I've got x equals t. Okay? Z equals 6 minus 3 halves t. And now I'm going to go back to one of these equations and solve for y in terms of t as well. So watch this. So x plus y plus z equals 10. What's x? T plus y plus z, 6 minus 3 halves t equals 10. Everybody okay with this? So, solve for y. Y is equal to, subtract a 6, 4. Subtract a t, add a 3 to halves t. Y is equal to 4 plus 1/2 T. Okay? So here's the line of intersection between these two planes. The line of intersection is x equals t, y equals 4 plus 1/2 t, and z is equal to 6 minus 3/2 t. That's their line of intersection. Equation of a line of parametric form. Okay? What does this say? Now check this out. If that line, okay, is the intersection of the two planes, every point on that line must belong to both planes. Okay? So let's verify that. Let's take a couple of points. Let's take t equals 0. I get the point on this line of 0, 4, 6. That point should be on both those planes. Where did I start? Well, up here? Is this where I started with this thing? I guess. 0, 4, 6, 0, 4, 6, yes. 0, 4, 6, yes. That's a point on both planes. It's on this line. Take another point on this line. T equals 1. I get the point 1. Ugh. I don't want that one. I want t equals 2. I don't want these things, fractions here. 2. So x is 2. Y is 5. And it's 3. That's another point on the line. Verify that. 2, 5, 3. 2, 5, 3. Yes, 10. 2, 5, 3 gives me 2. And every point on the line is on both planes, showing that that line is the line of intersection. So what do you do for a line of intersection? You got the two equations of the plane. I don't know why I'm talking so fast. I got a bunch of time. All right. You got the two equations of the plane. All right. What do? Eliminate one of the variables by any means you can. I eliminated the y's. You could eliminate the z's, whatever. You could even eliminate the x's with a proper choice there. Solve for the one variable in terms of the other. Let that be a parameter. Solve for the second variable in terms of the parameter. Take those two and substitute back into the original. Solve for the third variable in terms of the parameter. You want to get each of these in terms of the parameter. That'll define the equation of a line. Boy, you guys all died in there, huh? It seems to me all the life came out of you. That's why I was talking so fast.
The
Dylan?
equation of the line is intersecting the plane.
It's the equation of the line where these two planes intersect. These two planes intersect in a line. That is the line where they intersect. Every point on that line belongs to both planes. What happened there, Liam? Did I suck the life out of you guys? Is that what happened there?
I'm now dragging along.
Yeah, that's what I get the impression for
We
just
need a
about
rain
everybody.
day.
What's that?
We need a rain day.
A rain day, yeah, I know. It's not going to be this Friday, but it's going to be the next Friday, I think. But I guess if it's going to be 100% chance of rain, even though it's 3 days away, but it sounds like it's going to definitely rain.
What are you supposed to be doing?
I just every so often I have to take a day off. Once a semester, I usually take a day off. Sometimes I don't take any days off. This semester, I think I need a day off in here somewhere, and where I will just go to Milford or Hammonasset or something with my camera. I would just do that. That's what I'll do. Because I think we're in good shape. I mean, if I thought we were in not good shape about covering the material, I wouldn't do that. But we're going to have our second test next Thursday. It's just ideal. Have the test Thursday and have the day off on Friday. That works. Okay, any questions? Lines of plane. Tomorrow we'll start services in space. We're rolling. See you. Whoa.